Swayam Prabha. Digital India. Educated India.
Let us start this part by describing the move instruction. So the move instruction is arguably the most versatile instruction in the x86 instruction set. So it can actually do a lot. So in terms of RISC instructions, it combines, it's a combination of three things. So so if you would recall, in the RISC instruction set, we used to have a move instruction which was nowhere as powerful as this. So the move instruction in the RISC instruction set was actually moving the value of a register or a constant to a register. So the CISC move instruction does that. So we can think of it as a RISC move plus it's also a load. So you can load a value from memory and put it in a register. And it's also a store. So it can store something from a register to a memory address. So the move instruction in x86 is equivalent to a RISC move, a load and a store all combined into one. So what is the semantics? The semantics is very simple. The semantics is that the move instruction takes two operands. The first operand is a source as well as a destination, right? So it can either be a register or a memory. The second operand is clearly a source. So it can be a register, a memory, or an immediate. So as discussed in some of the earlier slides, that most x86 instructions are actually in a two address format. They take two operands, and the first operand is both a source as well as a destination. So we shall see this is standard format for almost all instructions. So here the idea is like this. So but in the move, for the case of the move instruction, the duality of a source and a destination is not very important. So we'll not overstress on this aspect here. So let's consider an example. Let's say we write move MOV EAX, EBX. So in this case, this is very simple. That the first instruction is the destination. The first operand is the destination, and the second operand is the source. So we move a value, the source value, to the destination. The value of the source to the destination. So this is the move instruction is extremely versatile. Instead of this, I could have always written something of this type. So in this case, this is actually a memory address, right? So what we are doing is that we are reading from memory. The first thing that we are doing is we are computing the value of this expression by accessing the registers ESP and EAX. Then we are accessing memory. We are reading 4 bytes. And then we are saving those 4 bytes in the register EBX. So this is a load. I could have similarly just interchanged both and maybe just written so this actually would have been a store because we would have read the value of EBX and put it in a memory address. So the former is an example of a load and the latter is an example of a store. So the move instruction can move values between registers. It can move a value from a register to memory, which is the same as a store. It can move a value from memory to a register, which is the same as a load. So as you can see, we have pretty much combined the functionality of 3 RISC instructions: a normal register or constant move instruction, a load and a store instruction all into one, which makes this particular instruction very interesting because if we just know this, we'll be able to write a lot of assembly programs And mind you, the standard rules that we discussed in the last few slides still hold, which means that both the source operands cannot be memory locations. So which means that we can't use this instruction to move values between two memory locations. But other than that, we can easily achieve a load and a store, and every memory operand will have the following form. It will start with a left square bracket, end with a left square bracket, and the value of the memory address will be specified within the address, where we can have a base register, a scaled index, and an offset. And in x86 parlance, an offset is known as a displacement. Similarly, we have the move SX and move ZX instructions. So the regular move instruction assumes that the source and the destination are the same size. But the move SX and the move ZX instructions actually assume that the source and destination have different sizes. So let us consider this. So the generic semantics is that, let's say we are trying to, so this sort of has a slightly restricted semantics in the sense that the first operand can only be a register and the second one has to be a register or memory. So once this value is being moved over here, we can, for example, write move SX, EX, BX. So mind you, BX is a 16-bit register and EAX is a 32-bit register. So what we do is that we read the value of BX, and S stands for sign. So the S here stands for sign extend. So we extend the sign of BX, and then we save it in EAX. So the second operand in this case can be either 8 or 16 bits, that's fine. And we extend the sign of BX and save it in EAX. Similarly, we have the move ZX instruction, where we don't extend the sign but treat it as an unsigned number. So we zero extend it, which means that we add the MSB bits. Instead of them being replaced by the sign bit, they are replaced by the number 0, and this number is stored in the register EX. And so in this case also the second operand can be either 8 or 16 bits. But instead of extending the sign, we treat the number in the smaller register BX as unsigned and replace the MSB bits. Sorry, don't replace the MSB bits, but set the MSB bits to be 0. That's pretty much it. So it's a special kind of move instruction where we are moving from a source which has a less number of bits to a register that can accommodate more bits. So the question is that those extra bits, what should they be set to? These extra bits which are in the MSB position in the case of SX are set to the sign bit, and so which means that the value is maintained. In the case of ZX, they are set to zeros, which is an unsigned extension. Alright, so we have seen the move instruction, move SX and move ZX. So let's now take a look at the exchange instruction, XCHG. So the exchange instruction is also very important, but we will not be able to fully understand the meaning of an exchange instruction and why it is that important till we actually reach chapter 11. And even in chapter 11, we'll only discuss a little bit of it. So an exchange instruction is very useful while writing parallel programs. So we will discuss maybe a little bit of exchange over there. So the main idea is that exchange takes two arguments, two sources, which are also destinations, by the way. So for source 1 can be a register or memory, and source 2 can be a register or memory. I can maybe write S1 and S2. So for example, this can be, but mind you, both cannot be memory locations. So the same constraints still hold. So we can write exchange EAX and a memory location, EAX plus EDI in square brackets. So it will essentially swap or exchange the contents. So the contents of EAX will come here and the contents of this memory location will come into EAX. Right? So it will exchange the contents of EAX and EAX plus EDI. It will just swap the contents of operand 1 and 2. So what are the instructions you have seen up till now? We have seen the move series of instructions and exchange. Alright. So given the fact that we have seen this, there are some more instructions that we need to see to get a better idea of the memory and the data movement instructions. So two of those instructions are push and pop. So why do we have this? The reason we have this is because an x86 processor is explicitly aware of the stack, unlike simple RISC where that was not the case. So an x86 processor is aware that the stack pointer is stored in the register ESP, and so that's the reason it defines two instructions called push and pop, which take a single operand. So let's consider the push instruction. It takes a single operand. The operand can be a register, can be a memory, or an immediate value, a constant. So for example, we can say you push ECX on the stack. In this case, the value of, so this is similar to this small code snippet over here. This is exactly what the processor would do. So given the fact that this is a CISC instruction set, a single instruction can actually do a lot. A single instruction can do the same as 4 or 5 equivalent RISC instructions, maybe sometimes even more. So what we would do is first we'll read the value of ECX, put it in a temp value. Then we will decrement the stack pointer by 4, right? Because we are pushing it and assuming a downward growing stack. And then the value of, then what we will do is that we will access the new stack location and put in the value of ECX. Now let's consider the pop instruction. So the pop instruction does the reverse. So that's the reason. So we'll see in the explanation that the same sequence of steps are just written in reverse to make the understanding easier. So in the pop case, we can pop the value from the top of the stack and put it in a register or memory. For example, let's say pop ECX. So just, these statements are in reverse. So first we read the value under the stack pointer into a temporary variable. So this is sort of an equivalent programmatic explanation of what pop would do. Then we increment the stack pointer, and then what we had read from the stack, we assign that to ECX. And it's definitely possible to write this program without the temp variable, but it has just been done to show the order of actions of what exactly the processor would internally do. And but definitely we can make the program simpler if some of you are not happy with 3 sub instructions. We can replace it with 2, but the basic idea would still remain the same, that we push the value onto the stack and change the stack pointer. While pushing we decrement it, and while popping we increment the stack pointer. So specifying memory operand sizes, so let's take a look at it. So the processor knows the size of a register operand from the name of the register. For example, EAX is a 32-bit operand, we know that. AX is a 16-bit operand, we know that. And RAX is a 64-bit operand, we also know that. But what about memory operands? So let's take a look at some instruction of the form push EAX. So in this case, we read the value of EAX, we get a 32-bit memory address. We access memory, we read some bytes and push them onto the stack. But the question is, how many bytes need to be pushed? Is it 2 bytes, 4 bytes, 8 bytes? How many bytes? So that's the reason it is necessary to provide a modifier to the push instruction, such that especially when we are trying to push something into a memory address, we can specify how many bytes need to be pushed. This is not necessary for a register, but for a memory operand this is necessary. So in this case we'll actually push 32 bits because we are using the D modifier, and D means 4 bytes or 32 bits. Similarly, we need to use modifiers for other instructions such as pop when the number of bytes that need to be transformed or transferred are not known. In the case of a register, since we know its size, we are assuming that we'll fill up the entire register. But in the case where we are not really sure because we are transferring something from the stack to another memory location, we do not know for sure. So that's the reason it is necessary to use this particular modifier over here, such as dword, to say that we want to push 32 bits. Let me now discuss some of the common modifiers. Depending upon the size, depending upon the number of bits that need to be transferred from memory, we can use different kinds of modifiers with instructions that access memory. The first modifier is byte, so it specifies that 8 bits or 1 byte needs to be transferred. The second modifier is word, so it means that 16 bits need to be transferred. So I need to make a point here. In simple RISC and in ARM, we assume that a word is 32 bits or 4 bytes. So this is not correct in x86 because of historical reasons. So in x86, a word is assumed to be 16 bits or 2 bytes. So this is what a word means in the context of x86. So we use the modifier dword or double word in the last slide, slide number 27. In this case, we assume that we are transferring 4 bytes or 32 bits. To support the newest and latest 64-bit instruction set, we have the modifier qword, which is quad word or 8 bytes or 64 bits. So after we have seen this, let's take a look at this example over here, which I have deliberately chosen as a slightly complicated example. So we will take a look at 4 x86 assembly statements, and at the end we need to answer this question: what is the value of EBX after these 4 instructions? So let's not take a look at the answer just right now. So let me maybe give you 10 seconds for you to take a look at these 4 instructions and work it out. And after that, I'll work out each and every instruction and show you the steps. Alright, so let's see. So the first instruction sets the register EAX to 10. So this is nice and straightforward. The second instruction moves EAX to the location that the stack pointer points to. So let's say the stack pointer points to this location, and since it's a downward growing stack which grows downwards towards lower memory addresses, what we do here is that we save the value of EAX, which is 10, to the location pointed to by the stack pointer. Subsequently, what we do is that we take the value that is contained in the location that the stack pointer points to and push it again on the stack. So this particular instruction is complicated, so I would like the readers to pay special attention. So here what we do, so the first thing in any push instruction is we see what is the value of the argument, what is it that needs to be pushed. So what needs to be pushed is a dword or a double word or 4 bytes. So we need to read 4 bytes from the current stack pointer. So the current stack pointer contains 10. So essentially we are pushing 10. So what we do now, so if you take a look at the pseudocode of push that was explained a couple of slides ago, what we now need to do is that we need to decrement the stack pointer by 4 in the new location, which is the next location on the stack. We need to push the value of 10, which is what we just read. Subsequently, the next instruction. Now what is the current status? The current status is that the stack pointer points to this location, which is the next location. So let's assume that the memory address, the previous memory address of the stack pointer was 1000. So the current memory address of the stack pointer is 1004. So the next instruction, the last instruction, reads the contents of the memory address the stack pointer points to, which in this case is 10, and the value of 10 is transferred to EBX. So what is the value of EBX at the end of this code snippet? It is 10. So the important point to remember is that in any push instruction, we first read the value of the operand that we are trying to push. Then we decrement the stack pointer, and essentially in the new stack top, at the new stack top, we push in the value. So this instruction, I deliberately made it complex. And what was the complexity? The complexity was that the argument of the push instruction was a memory address that was determined by the current value of the stack pointers. It's just to ensure that the understanding is clear. So let me just go back to the point where we defined the push instructions. If you see here, we first read the value of the push argument, whatever is being pushed, into a temporary variable. Then we subtract the stack pointer, and at the new location we push in this. So the advantage of this is that just in case this argument contains the stack pointer, it will get taken care of, as we saw in this particular example. Alright, so now that we have taken a look at the memory instructions, so the memory instructions are basically move and its variants, exchange, push and pop. Right, so let me just write it, let me just go back to the previous slide and write all the instructions that we have seen up till now. So we have seen move, and we have additionally seen two of its variants, SX and ZX. We have also seen the exchange instruction that exchanges the values at two locations. And then we have seen the push and pop instructions that are explicitly for dealing with the stack. The interesting thing is that in x86, the hardware is explicitly aware of the stack and it uses the stack pointer. This was not the case in other architectures, not in Simple RISC and ARM. But in this case, the push instruction actually reads the stack pointer, decrements it, which is good. So now let's take a look at ALU instructions. ALU instructions follow exactly the same format as we had discussed earlier when we gave the generic format of two address instructions. So they take two operands. The first operand is the first source as well as the destination. The second operand is the second source. So the first operand can be either a register or a memory. The second operand can either be a register or a memory or an immediate or a constant. For example, if we have add EAX, EBX, in this case the explanation is that we are setting EAX equal to EAX plus EBX. So mind you, the same rules hold. The rules are that both these operands, both the source operands S1 and S2 cannot be memory operands. Only one of them can be a memory operand. That's the first rule that we talked about. And also the second rule is that the first operand is a source as well as a destination. So the subtract instruction is similar, it's add and sub. So the names are also similar. And so here also we set EAX equal to EAX minus EBX. Similar to ARM, so in ARM, recall that we had two instructions where we were able to add with a carry or subtract with a borrow. So x86 is very similar. It also has the ADC instruction. The ADC instruction, ADC EAX EBX, will essentially set first add EAX plus EBX, then add the value of the carry bit. So this is just to ensure that we can add very large numbers, even if they don't fit within a register. So we can add two pair of numbers. We can add two numbers or a single pair of numbers. Then the carry bit can be saved and it can be used in a future addition. So that's the reason this particular instruction is EAX plus EBX plus the value of the carry bit. So SBB the same thing. The ADC is add with carry and SBB is subtract with borrow. So let's consider an example, SBB EAX EBX. So we are setting EAX as EAX minus EBX. and this is minus the carry bit. So in this case, the carry bit actually works as the borrow bit. So unlike ARM in x86, the carry bit and the borrow bit are the same and have the same connotation. So basically what do? We first do a regular subtraction and then we subtract the borrow bit. We call it the carry bit, but it can be interpreted as the borrow bit as well. So we do the subtraction in that manner. So since this part we have seen earlier also in chapter 4, and for those readers who have not read chapter 4, let me just explain once again. So the main advantage of ADC and SPB is to ensure that we can add numbers that are much larger, add or subtract numbers that are much larger than 4 bytes in the case of a 32-bit OS. How would we do that? We'll essentially save the numbers in a set of registers, add one pair, and then save the carry, use the carry to add the second pair, and so on. Uh, all right. So let's now take a look at some simple one address single operand instructions in the one address format. So these are very handy and useful actually. So the instructions are inc for increment, dec for decrement, and neg for negative. So they take a register or a memory as an argument. So in one case we increment the value of the register or the memory location by 1. In the case of dec we subtract, and in the case of neg, what do? We multiply the number with -1. So let's consider an example. Nothing is complete without it. Let's write an x86 assembly code snippet to compute EAX is equal to -1 times EAX plus 1. So in this case, what do? Since the value of EAX is changing, what we do is that we first increment EAX, which means setting EAX to EAX plus 1, and then we call neg EAX, which means subtract EAX plus 1 with -1. Alright, now let's take a look at the compare instruction. We always have a compare instruction. We have to have rather a compare instruction. We can't live without it. So a compare instruction's job is exactly the same as was the case in simple RISC and ARM. So here we compare two operands. So in this case, source 1 and source 2. So the first operand can either be a register or memory. The second operand can either be a register or memory or an immediate. So we need to compare both of them and save the results in the flags register, which as we saw comes with different names: flags for 16-bit, E flags for 32 bits, and R flags for 64 bits. So in this case, if we are comparing EAX and EBX plus 4, so EBX plus 4 is actually the memory address. We are comparing the contents at this memory address. So we compare both the values in EAX and EBX plus 4, the memory operand corresponding to EBX plus 4, and we set the flags. Similarly, we can compare with an immediate also. So we compare the contents of ECX with 10 and we set the flags. Alright, now let's take a look at multiplication and division instructions. These instructions are always complicated, but they are not all that difficult. They are similar to ARM, but there are certain complexities involved. So let's take a look at the IMUL instruction in the single address format. So in the single operand form, in the one operand form, which is the first one, what do we have? So what we do is that if we call IMUL ECX, so by default it multiplies the value in EAX with that of ECX. So that is a default behavior, that whatever is there in EAX, it will multiply it with ECX. So now in the case of a 32-bit instruction set, the value of EAX is 32 bits and the value of ECX is also being put into 32 bits. So you can see that the product can in theory be a large number, right? So how large can the product be? Let's assume it is 2's complement. So basically in a 2's complement system, If we multiply minus 2 to the power 31 with minus 2 to the power 31, it is 2 to the power 62. So pretty much the product has to be represented in this case 63 bits. 63 is a bad number, so let's take 64 bits, a power of 2. So basically it is, we will, unless we allocate 64 bits, there is a chance that we'll have an overflow if we multiply two numbers, which is the problem. So in the single operand form, what we will do is we'll multiply whatever is the value given with the value stored in EAX. The final product will be 64 bits, and we will save the upper 32 bits in EDX, and we'll save the lower 32 bits in EAX. Alright, so what are we doing? We are multiplying in this example EAX with ECX. So assume EAX contains the value 17 and ECX contains the value 1000. We'll represent the product as a 64-bit number. Alright, so the 64 bits is 8 bytes. So the upper 4 bytes, we'll have an upper 4 bytes and a lower 4 bytes, right? Most significant 4 bytes and least significant 4 bytes. So the upper 4 bytes will get saved in EDX and the lower 4 bytes get saved in EAX. Alright, let's now consider the two operand form. So the two operand form given in the next slide basically multiplies, takes one register as the first source, and then it multiplies the register with either the contents of a register or a memory. So we multiply ECX with EX plus 4, this is the memory address, the contents of it. So in this case, what we do is that we don't save a 64-bit product. Rather, what we do is we treat it as a regular instruction, an absolutely regular instruction similar to add and subtract and so on, right? So in this case, we'll just set ECX as ECX times EAX plus 4. If there is an overflow, the overflow flag will be set. But we'll not save a 64-bit product. We will simply take the first register, treat it as the first register in this case is a source as well as a destination, as has been the case for other ALU arithmetic logical instructions. So what we do is that we take the first and second sources, multiply them and save them at the location of the first operand. Now let's consider a three operand form of the IMUL integer mul instruction. So in this case we have a register. The first operand is a register. The second operand is a register or a memory location. The third operand is an immediate. So in this case, so since it's a CISC instruction set, we can take the liberty of having a lot of instructions, a lot of different instruction formats, pretty much, whatever suits us. So in this case, what we do is that the first operand is the destination. Then we'll have source 1, the first source, and the second source. So what we do here is that this is the first source operand. We multiply this with 5 because the last one is an immediate. So we multiply the first source with 5, which is an immediate. And then we store the result in the first operand, which is a register. So these are pretty much the three variants of the IMUL instruction. So as you see, these three variants were chosen with a lot of care and thoughtful consideration. The first variant was chosen because in some cases we might want to store a 64-bit product, and so that additional facility was given, and this facility is there in the ARM instruction set as well. In the second case, we want to treat implement an IMUL instruction the same way as we have been implementing other instructions like add and subtract. In the third case, designers realized that maybe it is very common that you multiply the contents of a register or memory with an immediate and save it in another register. So we should have an instruction for it. So that's the reason they have an instruction for it. All right, let's take a look at the IDIV instruction, which is definitely complicated. So let's go back. As you see, IDIV instruction takes a single argument, and this is exactly what we'll expand in the next slide. So the IDIV instruction, the integer divide instruction, which is complicated, we shall see why. And this is also one reason why the original designers of the ARM instruction set, for the early ARM instruction sets, not the later ones, did not have a divide instruction because it is somewhat complicated. And we'll see why, and we'll also correlate this with what we had done in simple RISC to sort of resolve the issue. So here the idea is that we take a single argument which can be a register or memory. So what would an example be? Something like IDIV EBX. So so what we do is that we consider a 64-bit number in the case of a 32-bit instruction set, where the number is stored in EDX and EAX. So EDX stores the upper 4 bytes, EAX stores the lower 4 bytes, right? So see, the logic is similar. If you multiply two 4-byte numbers, the product can at most be 8 bytes, right? So here what we do is that that's the reason, consider a larger number and divide it by a smaller number. And it's sort of an exact analog of the single address form of the IMAL instruction, where we're assuming that the dividend, the number that we will divide, is an 8-bit number. It's stored in EDX and EAX with the upper 4 bytes. So let me maybe draw it. It'll be easier to understand that way. If this is the dividend, we are assuming that the dividend itself in this case meaning the 32-bit instruction case, is 8 bytes. The upper 4 bytes are in EDX. The lower 4 bytes are in EAX. Now in this case we are dividing it by the so what is the divisor? The divisor is this argument, which in this case is EVX, right? So the divisor is source 1. So once we divide, so the main difficulty in a division instruction is that a division instruction actually produces two results. So let's try to divide, integer divide, 10 divided by 7. So in this case, there are two results. One is the quotient, which is 1. The other is the remainder, which is 3. Similarly, another example, 15 divided by 7, quotient is 2 and remainder is 1. So as we can see, there are two results. So essentially we need two registers to store them. One register to store the quotient and one register to store the remainder. So this makes our life very simple. So by default, EAX will store the quotient after an IDIV instruction, and EDX will contain the remainders. You can sort of think as EAX and EDX as a pair. That will come together very, very often. And so in this case, EDX and EAX are containing the dividend. Then they are getting overwritten. So EAX will ultimately contain the quotient at the end, and EDX will contain the remainder. Alright, so let me just summarize what's written here. The dividend is contained in EDX EAX. In a 32-bit instruction set, EDX contains the upper 32 bits, EAX contains the lower 32 bits. The input operand contains the divisor. So which is basically either a register or a memory address. After the end of the division, EAX will contain the quotient, EDX will contain the remainder. Right, so this is very simple, but here is one mistake that most students do, and this is a very, 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 very important point to keep in mind. So let me put a star, and this is so important, let me put one more star. Right, so let me also write important, just in case, So basically, what is the idea? The idea is if the dividend is positive, so let's assume the dividend is 10. So in this case, EDX would contain all zeros and EAX would contain 10, and let's write 10 in hex, which is 0xa. What if we have a number? So we have inside EAX, we have minus 10. What do we do then? So here is the mistake that students do. What should EDX contain? What EDX should contain is that EDX should contain all ones, because we are essentially sign extending the number or extending the sign of the number, which in this case is minus 10. Minus 10 represented in binary, of course. So we are extending its sign from 32 bits to 64 bits. So that's the reason EDX should contain all ones, right? And if this is not the case, then we will have a lot of trouble. In the sense, if we set EDX to all zeros, that's going to be wrong. And this is a large source of bugs in the IDIV instruction. And setting any number to all ones is actually very easy. All that we do is move EDX minus 1. This is all that needs to be done. So if a number is negative and it is fitting within 32 bits and the number is within EAX, all that needs to be done in the case of a negative dividend is that we need to extend the sign of EAX. So if EAX is positive, what we do is that we set EDX to 0, and if EAX is then negative, what we do is that we set EDX to all ones, extend the sign of EAX pretty much, and the way that this can be done is we move minus 1 into EDX. So this is very, very important. It's a big source of bugs, so I request all readers, listeners to keep this in mind. Alright, so the learning is never complete without an example. So let's write an assembly code snippet to divide minus 50 by 3, and let us save the quotient in EAX and the remainder in EDX. So minus 50, what do we need to do? We move minus 50 into EAX, we extend its sign, we move minus 1 into EDX, we move 3 into EBX, and we call the IDIV instruction on EBX. Automatically, the EAX will contain the quotient, which in this case is minus 3, and EDX will contain the remainder, which in this case is minus 2. Alright, so now let's take a look at logical instructions. So logical instructions will do a Boolean bit manipulation. So logical instructions that we have are standard instructions that we have seen in the case of simple RISC and in the case of ARM also. So they are AND, OR, and XOR. So these are the standard logical instructions that take two source operands. And we have the NOT instruction, which takes a single source operand. So the way that they work is very similar. The AND, OR, and XOR instructions work exactly the same way as their other arithmetic counterparts such as add and sub work. So the format is exactly the same. The NOT instruction works the same way as INC and DEC and other single source arithmetic instructions. So in this case, NOT of EAX would basically take the value of EAX, compute a bitwise complement, and store it in EAX itself. Alright, now let's take a look at shift instructions. So similar to simple RISC and ARM, so I'm deliberately going slightly fast here because my assumption here is that readers have an idea of what shift instructions are. And so this idea has come from chapters 2 and chapter 3. Because, I have been saying all the time, it's not possible to explain the concepts or the fundamentals of assembly language and a complex assembly language together at the same time. It will just make understanding very hard. So if listeners are still having difficulty, they can always go back to chapter 3 where simple risk was introduced, take a look at shift instructions and come back. So we have three shift instructions. One is an SAR instruction, which is a arithmetic shift right, shift arithmetic right, which is essentially the same as dividing a number by a power of 2. So in this case, what we do is that the format is that the first operand, which is the source as well as the destination, can be shifted with an immediate number, which is a number of positions that you need to shift with. For example, writing SAR EAX3 will set EAX to EAX right shifted by 3 places. Similarly, we have the SHR, which is the logical shift right, which is the same as dividing the unsigned representation by a power of 2. So let me write maybe unsigned. So in this case, we have always been using the 3 right arrow convention. So the format is exactly the same, SHR EAX3 as an example. Here we set the value of EAX, the EAX right shifted in a logical manner where the MSBs are being replaced with zeros, not the sign bit. Alright. Then the shift left instruction does not have an arithmetic and logical counterpart. It is only one instruction. So the one instruction has actually two codes and both of them are equivalent. SAL and SHL, essentially they're the same instruction. So this can be arithmetic left and logical left are the same. So the same instruction, SAL or SHL. Format is the same. First operand can be a register memory and the second operand can be an immediate. So what we do is we do a logical shift left. We take the register and we take a number. We set the register as EAX left shifted by 2 places. So we use the left shift operand here. So it is important that the second operand, the shift amount, needs to be an immediate. So nothing is again complete without an example. So what is the output of this particular code snippet? So let us consider this is a hex number actually. It sounds like an English word. But if we take a look, each and every digit over here is a hexadecimal digit. So it is dead feed. So let us move this to EAX and let us shift it to the right by 4 places. So 4 places means pretty much by 1 hex digit. So then the remaining, the 7 digits at the end become dead fee. The question is, what is the MSB? So this is easy to find out because D is actually 13 and 13's representation is 1101. So the MSB is 1. Say the MSB is 1, we in the case of an arithmetic shift right, we just replicate the MSB. So we put in an F, which is 4 ones. Now let's do the same thing but with a logical shift right. In this case, the only difference is that the most significant digit is actually 0. So the answer is 0x0 dead fee. Since 0 need not be explicitly mentioned, we have not mentioned it. So the answer is 0x dead fee. Alright, so now we have taken a look at the machine model of x86, simple integer instructions. So now we will proceed and take a look at branch instructions. The first thing that we need to note about x86's branch instructions is that branches are actually called jumps. Anyway, there is nothing in a name. As Shakespeare says, call a rose a chrysanthemum. A rose will remain a rose, a branch will remain a branch. So branches pretty much work the same way as they worked in simple RISC and in ARM. So here we have the jump instruction, which is the unconditional branch. So we always jump to a label, and the label essentially indicates the instruction that we want to jump to. So in this case, if you are jumping to label.foo, it essentially means that we are jumping to the instruction that is pointed to by the label .foo. x86 also has a lot of conditional instructions. So, I'm sorry, conditional branches. So, conditional branches are very similar. So, recall that in ARM and simple and x86, sorry, in ARM and simple RISC, the conditional branches were the form B and then the condition code. So they were instructions of the form B, Q, B, N, E, and so on. So in this case, instead of a B, we have a J. So an instruction of the form J, E, Q basically means a jump if equal. And equal, so where does equal come from? Well, the last instruction that has set the flags. So basically, there are some flag setting instructions. Compare is one of those instructions which can set the flags. After that, there can be many instructions. If these instructions, the only condition is that they should not set the flag for this example, then we have JEQ and then the name of a label. So if the compare instruction here led to an equality, then the JEQ condition will be true and we will branch to the label .foo. Otherwise, the program will just fall through in a sense that the next instruction will be executed. So there are many kinds of conditions. The same way as in ARM, we had 15 conditions. We have many conditions also in x86. So the condition codes are like this. So all of these conditions codes come after J. For example, JO would mean that branch if there has been an overflow, right, in the last instruction which is doing some kind of an arithmetic operation. Similarly, JNO means no overflow. There are some comparison operators for unsigned comparison. So for unsigned less than, that is called below. So JB basically means jump if it's less than in an unsigned sense. And NB means not below. Then we have two conditions E and Z which are actually the same conditions. So they can be used interchangeably, no problem in that. JE and JZ, which means that the last comparison or the last flag setting instruction should have resulted in an equality. So recall that how do we check for equality? Essentially, when we are comparing two values A and B, when two values A and B are being compared, what the processor actually does is that it subtracts B from A. So it computes A minus B. So if A minus B is equal to 0, it essentially means that A is equal to B. So we have equality here and it is same as A minus B being equal to 0. So equal or 0 is sort of the same condition. There are other flag setting instructions as well. So essentially there we see the value of the result. If the result is 0, this particular flag will be set. So the opposite of E and Z is NE and NZ. So that is, we'll have two instructions JNE and JNZ which are also totally equivalent. So we introduce the B flag here below unsigned less than. So BE is below or equal, unsigned less than or equal. So now we have, so after these comparisons, we have another class of condition codes. The condition codes are S and NS. So S basically means the sign bit is 1, or alternatively the number is negative. NS means that the sign bit is 0, which means that the number is 0 or positive. So recall that we had similar flags in ARM also, PL and MI. So we have very similar flags in x86. So this is the similarity between the instruction sets between simple RISC, ARM and x86. So what we get to see over here is that most of the core mechanisms such that branches and condition codes are similar, and to a large extent they are also inspired from some earlier designs. But the basic point to note is that the difference between instruction sets in a lot of cases is only superficial. A lot of their fundamental underlying mechanisms are still the same. Now we have some signed operators, L and LE. So L means less than, signed less than. This is a signed comparison. LE means less than or equal, signed. G and GE mean greater than and greater than or equal. Alright, so basically a branch of the form JG would mean jump if greater than, and JGE would mean jump if greater than or equal in a signed sense. So now that we have seen these basic condition codes, we are all set to write a program. And so this is an assembly program. My assumption here again is that readers have some familiarity of assembly programs from chapter 3. Otherwise, this program, I'll still explain all the steps, but it might be slightly difficult. So the example here is test if a number in EAX is prime, and they put the result back in EAX. So result, what is the result typically? It's a Boolean result. If the number is prime, you essentially put 1, right? 1 indicates that the number is prime, and 0 indicates that the number is not prime. So that's a Boolean result. All right. So what do we do? So what is the basic algorithm? How do we find if a number is prime or not? So what we do is, let's say given a number n. So here the assumption is the number is large enough. So we don't want any corner cases. So given a number n, we divide it by 2, we divide it by 3. So we keep on dividing it till we reach n minus 1. If any one of the remainders of these divisions is 0, this means that it has a factor, and which is not either 1 or n itself. As a result, the number is not prime. So let's start with the first index, which is 2. So I'm setting EBX equal to 2. So now the original number, which we need to test if it is prime or not, we are transferring that to ECX. So ECX will contain the original number, and then we start a loop. So what we do is that since the original number is in EAX now, so this is required for correct division. So recall that the IDIV instruction actually needs a 64-bit number in EDX and EAX. So what we do is, since the original number is in EAX also, we can go ahead with the division, but we need to set EDX. When the number is positive, the value of EDX will be 0 because we are just extending the sign of a positive number, and the sign bit of a positive number is 0. So we move 0 to EDX. This is needed for division, and then we go ahead with the divide, and we divide it with the value stored in EBX, which is 2 for the first iteration. Subsequently, we take a look at the remainder, which is stored in EDX. So we compare this with 0. If it is 0, which means JE, we jump to dot not prime. So not prime, the answer is very simple. We move 0 to EX, which means the number is not prime, and we exit. Otherwise, we increment EBX. So from 2, this will become 3 and 4 and 5 and so on. Then the value of EAX has also changed because the IDIV instruction puts the quotient in EAX. So recall that the quotient is being put in EAX and the remainder is being put in EDX. So what we do is, since the value of EAX has changed, we put back set the original value of EAX again. We're transferring the contents of ECX back to EAX. So EAX gets restored. Then we compare EBX and EAX, which is essentially the index and the original number. As long as the index that we are dividing the original number by, the divisor, is less than the original number, JL, we jump back over here. Jump if less than, so we jump back over here. Otherwise, we reach the end of the loop. At this point, we can compute that since we didn't find any factors, the number is prime. We put 1 there and we jump to exit, which means we move out of the program. So this program is simple. The program is not very difficult. In terms of assembly statements, how many do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we have 13 assembly statements. It's not that difficult. And now, after I've explained to it, it must be appearing slightly more straightforward. But the question is that can students who are listening to this lecture, can they write such a program from scratch? Right? Given any problem, can they write such a program? And that is unfortunately not going to come by listening to such lectures or reading books. The only way that it's going to actually happen is by practicing as much as possible. Because all of these things are pretty much a function of practice. So what listeners need to do is that they need to write hundreds of assembly programs such that they can write fairly good bug-free code almost all the time in a very repeatable, reproducible fashion. So let's move ahead. So what's left? What is left is function call and return instructions. So the call and return instructions are exactly the same as simple disk with some differences. So the differences are like this. So let's first find out what is similar. So what is similar is, so we have a call instruction. We always, the format is call and a label. So let's say we go to label.foo. .foo is the beginning of the function, right? And recall that what were simple disk and ARM doing? What they were doing, so a call instruction is just not a jump. Something needs to be done with the return address. So what simple disk and ARM were doing is that the return address was, so basically call has something to do with the return address. So return address in those ISAs was being put in the return address register. x86 does not do that. It is rather stack based, so it pushes the return address on the stack. So it knows the value, it knows which register contains the stack pointer. So it pushes the value of the return address that is on the stack, and then it jumps to the label.foo. Similarly, we have a zero address format instruction called ret. So here we return to the address that is saved on the top of the stack and we pop the entry. So it's completely a stack based system. So assume that this is the stack and then we have a call. So the return address gets saved on the top of the stack and then we keep moving. Finally, what we need to do is we need to kill the stack. The return instruction will take the value of the return address and pop the stack. Alright. So what does a typical function in x86 do? So well, it needs to do similar things. So we recall that we have discussed everything about functions in chapter 3. So the idea is that first, before calling a function, we need to put all the arguments and so on the stack or in registers. So once a function begins, it extracts the arguments from the stack. It creates space on the stack to store its own activation block. It spills registers if required. So there, the issue of caller saved and callee saved comes into play. It calls other functions, does whatever processing. So it does its own logic. It implements its own logic. Finally, after doing that, it puts the return values either in designated places in memory or in registers. It restores the stack pointer and it returns. Alright, so now let's take a look at an example. So this is the example. So the idea here is to write a recursive function. So users might wonder that why do we always give recursive functions as examples? Well, our aim of giving an example is to give the most difficult examples. So I said a difficult example will hopefully stimulate the reader to go into depth. So the idea here is write a recursive function to compute the factorial of a number which is greater than or equal to 1, and the number is stored in EAX and save the result in EBX. So essentially compute EAX factorial, save it in EBX. And the function has to be recursive. What does recursive function mean? It basically means that the function is calling itself. Alright, so let's start. So the name of the function is factorial. So we'll start, so whenever we jump, we'll essentially jump to this point. So here we put 1 in EBX. So this is the default return value. So recall that 0 factorial is 1. So maybe I can write it over here. 0 factorial is, what is this? This is essentially equal to 1. 1 factorial is also equal to 1. Right? So basically the default return value, we put it in EBX. And then we compare EAX with 1. If so JZ, it can be JZ here or JE, it doesn't matter at all. So if there is equality, we return. So we return if the input is equal to 1. So which means that the answer is 1. So we can just return and the answer will be there in EBX. Otherwise, we go to the recursive step. So in the recursive step, we push the value of EAX, which is the value, the number n, right, that we got. So we are actually calling it num over here. So the number num on the stack. We decrement EX and then we call the factorial function. After calling the factorial function, what is the expectation? The expectation is so the reason this is made in red is because this is these are the important instructions. So the expectation is that EBX will contain n minus 1 factorial. So what do we do now? We pop EX, so bring it, read it back from the stack, and we multiply. So what does EX contain at this point? EX contains the number n. And what does the EBX contain? EBX contains n minus 1 factorial times n. So we multiply n minus factorial times n. So EBX will now contain n factorial, right? A regular multiply instruction, and then we return. So this is a simple. It's a very simple function where we have a single push and a single pop. And what is the reason for actually pushing EX? Because we are changing its value and we are sending it to another function, and we need the value at the end. So you can think of this as, well, it can be either, since only one value is being used, it doesn't matter if it's caller saved or callee saved, but essentially the value of EAX is required and the value is being changed. So before calling the function, we essentially store it on the stack and later on restore it. The reason the ret function works is because we are otherwise every push has a has an accompanying pop instruction. So the size of the stack is otherwise not being changed. So when we do a ret instruction, when we call the ret instruction, it will find the return address at the stack top, which is this point. It will pop the return address and go back to its original parent function. So this is a simple program. It has 3, 4, 5, 6, 7, 8 and 9 instructions to compute the factorial. Even if I were to write it in C, it would still take 3-4 lines depending upon how we count. So x86 assembly in that sense is not all that inefficient. It has many instructions, so a lot of cool things can be done. It also has conditional instructions similar to ARM, for example in conditional add or so on. So they are called CMOV instructions. So I'm not discussing them. So you can see the x86 manual that has hundreds of instructions, and a lot of them have very cool features. But I'm only discussing the main instructions. So here, what's the trick? Well, there are hardly any important tricks. The only trick is we are using the IML instruction and we are pushing and saving and restoring the value of EAX via the stack. Those are the only take-home points from this algorithm. So implementing a function, what do? We use push and pop instructions in small functions like the one that we showed, uh, which is fine because it worked. So if you see in the last one, we used a push instruction and a pop. For large functions that have lots of internal variables and arguments, it might be necessary to push and pop a lot of values from the stack. Fair enough. For languages such as C++ that dynamically declare local variables, so what you have is in languages like C++, a lot of local variables can be declared even within the body of the function. So it sometimes becomes difficult to keep track of the size of the activation block, because even at compile time we would not know what is the size of the activation block, right? How many internal variables of the function actually use. So at runtime, the size of the stack needs to be varied. So x86 processors have a mechanism of doing this. So what they do is that this is where we use the EBP register. So we save the starting value of ESP. So whenever we enter a function, the value of the stack pointer is called the starting value. So we save the starting value of ESP in the EBP register. So the stack pointer is stored in the base pointer register. So let me, maybe this might require a little bit of explanation. So whenever we start a function, the first thing that we do is that we set the EBP equal to the ESP, and then we keep on growing the stack. There are a lot of instructions. At the end, to restore the stack pointer back, all that we do is ESP is equal to EBP. So that keeps our life very simple. Because note that in x86, or in fact in any other assembly language, before leaving a function we need to kill the activation block. Killing the activation block is same as restoring the stack pointer. So let me write it killing. It shouldn't be killing, it should actually be deleting, but that's okay. Maybe deleting. Is the same as restoring the stack pointer. Alright, so let's write a recursive function for factorial without push and pop instructions, right? So let's not use any push and pop instructions, and let's write a recursive function for factorial. Alright, so let's do one thing. Let's assume that whoever calls the factorial function, it puts the value of EAX, which contains the number whose factorial needs to be computed, on the stack, right? So whatever is the stack pointer, on the stack pointer we do that. So the assumption in x86 is like this, slightly complicated. If this is the stack pointer, so if you read at the beginning of a function, if you read what is there inside the stack pointer, you'll only get the return address, because this is what is the last thing that is done before calling a function. The last thing that is done is that you'll have an instruction of the form call factorial, and immediately the control will jump to the factorial function, and that is when the return address will be pushed on the stack, and the stack pointer will point to it. Just above the return address, which means because the stack is downward growing, so pretty much at ESP plus 4, which is this address, we have the opportunity of pushing in arguments. So if we push in the value of EAX, we can, the moment we enter the factorial function, which is at this point, we can read ESP plus 4, the stack pointer plus 4. Its contents would contain the value of EAX, which is essentially the value of the number, and this we can transfer to the register EAX. So let me repeat. Consider the function that is calling the factorial function. What is the last thing that it will do before calling? It will invoke the call instruction. What does the call instruction do? The call instruction decrements the stack pointer and pushes the value of the return address on the stack. So before that, if we need to access the stack of the caller function, it is possible for the caller to push the value of EAX on the stack, which is push the value of any register or any memory address. But in this case, we are only concerned with EAX. So push the value of EAX, which is the number num, on the stack, and then invoke the call instruction. So when we reach here, ESP would point to the return address, but ESP plus 4 would point to a location within the caller's activation block, and there we can read the value of num and store it in EAX. Then what we can do, recall the star star star, which are the new instructions. We can push EBP. So we can store the value of the base pointer that was there and transfer the value of the stack pointer into the base pointer. Well, subsequent instructions are the same, setting the default return value, comparing the number with 1, jumping if there is an equality. This is all the same. Now let's come to the recursive step. In the recursive step, what I do is I create some space on the stack. So I subtract 8 from ESP, which gives me space to put in several things, put in 2 integers. So at ESP plus 4, what I do is I put in the value of EAX, which is the number. Then I decrement EAX. And at ESP, which is essentially, so let me consider if this is the stack pointer, what I do. So assume that this is the old value of the stack pointer, which is at this instruction, prior to this instruction. This is pointing over here. So if I subtract it by 8, I'm creating positions. I'm creating actually 2 spaces, 2 slots to save 2 integers, right? If I am subtracting it by 8. And a new stack pointer will point over here. So what I can do is at ESP plus 4, which is this location, let me save the value of the current number, right? And then at ESP, which is this location, let me decrement the number by 1 and save num minus 1. Right, it might not be visible, so I'll just write once again. Then I call the factorial function. What that would do is that would do exactly the same. Go to its ESP plus 4, which is this location. So basically what that would do is it will call the factorial function. So when you are calling the factorial function, what will the stack look like? At this point, when you are doing the call instruction, additionally the return address will be pushed, right? And the ESP, the stack pointer, will point over here. Inside the called function, we'll add 4 to ESP and read num minus 1 and compute its factorial. So after calling factorial, what do we need to do? We need to restore the value of EAX. So just take this instruction and flip the arguments. So ESP plus 4 is retrieving the input. Finally, we do the multiplication. Prod equals prod times num. Then we have these 2 extra lines here. So we restore the stack pointer. So basically whatever was there in EBP, we put it into ESP. And we restore the value of EBP by popping it. And we return. So in a nutshell, what did we achieve? This program is exactly the same as this program, right? But here the only difference is we are not using push and pop instructions. Instead, what we are doing is that we are explicitly managing the stack. So in terms of hardware performance, it will not be any different because push and pop instructions actually encapsulate a lot of functionality. So what we do is that we first, so the main magic lies here is that we create an activation block with space to store two integers. So let me call it the activation block. Activation block with space to store two integers. One of them is the ESP plus 4. So the new stack pointer would point over here, ESP. One of them is used for register spilling. So we are spilling the value of EAX, which essentially contains the original number. The other one is being used to pass an argument to the next function that will be called. So this has num minus 1, right? Only two things, right? In the activation block, this is a spilled register, and this is an argument for the next function that we are calling. Then we call the next function, it works in exactly the same way. Then we restore EAX and we multiply. So EBX at this point is supposed to contain n minus 1 factorial. EAX, so num minus 1, my mistake. Num minus 1 factorial, right? And EAX is supposed to contain num. We multiply and then we get num factorial. Subsequently, since we changed the stack pointer, whatever was the original value saved in EBP, we move it to ESP and we restore the value of the base pointer and we return. So what are the extra instructions? The extra instructions are these two, right? These two over here. And the instructions to create the activation block and manage it, which is subtract 8 from ESP and move EAX to ESP plus 4, move EAX to ESP and restore the value of EAX, right? Couple of extra instructions are there. So do we need that many extra instructions? If you see, we have 7 instructions that we are changing. Do we need them? The answer is probably no. So x86 is great in providing shortcuts. So the complexity that we saw in the last example, that will not happen. That's not required. We have an enter instruction. So what the enter instruction does is that it does a lot of things in one instruction. It pushes the value of EBP onto the stack, the value of the base pointer on the stack. It moves ESP to EBP, so saves the value of the stack pointer in the base pointer. And it subtracts from ESP whatever argument has been specified here. So here we have specified 32 bytes. So it will subtract 32 from ESP. So what is it doing? It's doing a lot of things. First, it is doing the job of pushing EBP, putting ESP to EBP, and so the job of this instruction, and this instruction are all being done by one instruction, which is essentially storing the value of EBP on the stack, setting EBP to the stack pointer, and creating the activation block by deleting the size, by subtracting the size of the activation block from the stack pointer. So this is like a 3-in-1 kind of instruction. Alright, so basically this is what it does: push EBP, move ESP to EBP, and subtract the stack size from ESP. It's a standard sequence of operations. So instead of having 3 instructions for it, the enter instruction will do actually all 3. Similarly, we have the leave instruction, which will do the reverse. So it will move the value of the base pointer into the stack pointer, or in other words, restore the value of the stack pointer. It will pop EBP, which means restore the value of the base pointer, which is also a standard sequence at the end of a function. Right? So what does the leave do? The leave instruction does the job of these 2 instructions over here. Restore the stack pointer and the base pointer. And the enter instruction does the job of actually storing the base pointer, setting the base pointer equal to the stack pointer, and creating the activation block. So pretty much these three instructions are folded into one instruction called enter. And the only argument, well, the two arguments, the second argument is slightly more complicated, but for all practical purposes, we always set it to 0. The first argument is the size of the activation block, which in this example is 32. So if we were to write this program, the previous program, what do we have to do? All that we have to do is we need to add only two instructions and remove all the other instructions. One instruction would be this, one more instruction would be this. So let me go back to the complicated figure that we have complicated by writing a lot of things. So essentially these three instructions get fused into one and these two get fused into one. So we call the enter instruction, which saves the base pointer and the stack pointer and also creates an activation block of size 8 bytes. The rest of the code is the same. Then we save the input on the stack, right? Saving the input on the stack is essentially same as spilling, right? So we know that the callee will change it. We are pretty much spilling it. And then decrementing EAX and pushing the argument, calling the function. All of this is fine. And at the end, we call the leave instruction, whose only job is to load or, well, instead of load, maybe the word restore would be better. So restore ESP and EBP. So now you see that push and pop are not always required. Well, they are good ideas if the program is small and simple. And recall that pushes and pops have to be exactly matched. So if we have n pushes, we need to have n pops, right? Otherwise, the stack will not remain the same and a return instruction will not work. And keeping track of the number of pushes and pops in a complex function is hard. That's the reason what you do is that you save the starting state at the beginning with the enter instruction. Then you do whatever you want to do with the stack. And just before leaving, call the leave instruction, which will restore the value of the stack pointer and the base pointer. And then you return. So why is this needed? The reason this is needed is basically because we want to completely delete the activation block. And when you return, the value of the stack pointer should be pointing to the return address, because that is where we will read the return address from. Alright, so after taking a look at enter and leave, so let me actually come back for 2 seconds with enter and leave, and then I'll again proceed further. So in complicated programs where a lot of variables are allocated space on the activation block, and the activation block per se, is a large structure. So let me call it the AB. And it can have like 100 integers or maybe more, right? So depending upon the paths that the program takes, the size of the activation block can vary. So instead of monitoring it in a very fine-grained manner, what is the ultimate thing that we need to ensure? That when the function returns, this entire structure is killed. This is exactly what the enter instruction and the leave instruction allow you to do. So using the enter as one of the first instructions in a function and leave as one of the last instructions, like the instruction just before ret, is actually a good idea and good x86 programming practice. Alright, so now we will discuss advanced memory instructions.